Hello everyone, I'm Chao Zhang, a fifth-year PhD student from Lehigh University. I'm excited to present our work RnR, a software-assisted record and replay hardware prefetcher. This is a collaborative work with my colleague Yuan Zhen, John Sharp from Lawrence Berkeley Lab, and my advisor Xiaochang Guo. As the amount of data and memory capacity increase, new algorithms and software are developed to solve the problems that were insurmountable before. These big data applications such as machine learning, numerical analysis, and web search tend to use a sparse data format to avoid storing zeros. As a result, the address patterns can be data-dependent and irregular. Modern processors have a gap between the processor and memory clock frequencies. Existing hardware techniques, such as caching and prefetching, that helps to bridge this gap does not work well for these big data applications due to their poor spatial and temporal locality in the memory access patterns. Among these big data and irregular applications, iterative algorithms are widely adopted in different domains. This is because directly solving these large problems is often impractical, and using iterative method can approximate the optimal solution in an acceptable amount of time. PageRank, community detection, belief propagation, and iterative solver are some of the examples. Most of these iterative algorithms takes more than 100 iterations before it converges. Even though the address pattern of these irregular applications are data-dependent, the patterns are typically repeating among iterations. This work will exploit these repeating irregular memory access patterns to improve the performance of these big data and irregular applications. Before we discuss the repeating patterns, let's take a look at graph traversal example to understand the irregular data access pattern and why existing prefetchers do not work well. Compressed data format such as compressed sparse row is typically used in graph applications. In this example, there are 5 vertices labeled from 1 to 5. The edge array records the destination vertices each source vertex connects to. For example, the 3 edges of node 1 connects to node 2, 3, and 4. The row pointer array stores the indices of the edge array that separate the edges among different source vertices. For example, the first value in row pointer array 2 means the vertex 4 in the edge array is a destination vertex of the last edge that belongs to vertex 1. If graph traversal order is 1, 2, 3, 4, and 5, for both row pointer and edge array, the X order is sequential and has a good spatial locality. Therefore, streaming prefetchers that simply predict the next few addresses can have good accuracy. However, for vertex array, the X order is irregular and depends on the value stored in the edge array. For graph algorithms, accessing the vertex array usually costs more than 90% of the last level cache misses. These irregular accesses are difficult to predict using existing hardware prefetchers. Here we list 4 types of widely used prefetchers. Streaming prefetcher generates prefetch addresses based on a fixed thread. Spatial prefetcher divides the memory space into multiple spatial regions and use common offset pattern to prefetch for the next spatial regions. Temporal prefetcher learns correlation between pair of addresses accessed in a sequence to predict future memory access. Indirect prefetcher relies on node dependencies from one data structure to another data structure to generate prefetching addresses. The last two seem to be able to predict well for irregular and iterative algorithms, but their accuracy and coverage are below 70% for PageRank with a real-world graph. The mispredict prefetchers can cause unnecessary data movement, and low coverage means there are still many cache misses that can cause processor to stop. This work aims to achieve close to 100% miss coverage and prefetching accuracy for irregular and iterative algorithms. Before we present the key idea, let's take a closer look at temporal prefetcher and indirect prefetcher. The managed irregular streaming buffer MISB is an example of temporal prefetcher designed for irregular memory access patterns. MISB manages metadata using program counter and memory addresses. If array A and B are fetched by different program counters, they can use different on-chip cache sets to store the correlation addresses. However, since the metadata is managed by address pairs, each address will only have one entry with each PC. For irregular applications such as graph analysis, this PC localization method cannot always differentiate similar access patterns. For example, when a vertex is shared destination of multiple source vertices, the substream of each PC can be similar but not the same. and this will cause mispredictions. In this example, the address b plus y is not always followed by the same temporal sequence when accessed with the same PC. The data-aware decoupled prefetcher droplet is an example of indirect prefetcher design for graph applications. It relies on low-dependency information to predict the next address. In the graph algorithm, the value in the edge array decides the vertex addresses that is going to be accessed. Therefore, droplet uses streaming prefetcher to prefetch edge array and calculate the corresponding vertex address based on the prefetch edge values. However, if the edge array is not accessed sequentially, an inaccurate edge prefetching will lead to an inaccurate vertex prefetching. In this example shown here, when edge array access a plus 3 is mispredicted, the following prefetching to the vertex array will be incorrect. To overcome the limitation of existing prefetchers, this work proposes a record and replay RnR prefetcher that liberates the iterative nature of irregular applications and programmer knowledge to improve the accuracy of hardware prefetching. A lightweight programming interface is used to allow a programmer to first identify which data structures suffer from irregular memory access to filter out irrelevant address ranges. The programmers can then identify correct program faces for recording and replaying the address patterns. To improve the replay prefetching timeliness, a replay timing control is designed to avoid prefetching too early or too late. The proposed RnR prefetcher can also easily combine with other prefetcher for regular access patterns. The motivation of the RnR prefetcher comes from many important iterative applications that run repeated kernels. Let's use PageRank as an example. The code snip shows the kernel. In the first iteration, the edge array is accessed in a streaming manner, whereas the vertex array p current is accessed irregularly. For the rest of the iteration before the algorithm converges, the same access sequences are repeated over and over again. To use the proposed RnR prefetcher effectively, the vertex array should be marked, and the irregular access sequence of this spatial region should be recorded during the first iteration and replayed for the rest of the iterations. For the data structure that access with streaming pattern, an existing streaming prefetcher can be used. The following slides will describe the proposed lightweight programming interface of RnR prefetchers to mark the data region and perform the record and replay. With the same PageRank example, the code snip shows when the kernel is evoked in a while loop. First, the RnR prefetcher is enabled before its kernel execution. Second, the p current is selected as data structure that suffers from irregular memory access. Third, the RnR prefetcher will set to start recording. At the end of each iteration, the RnR prefetcher will be set to restart the replay. After the application converts, the RnR prefetcher will set to stop replay. In the end, the RnR prefetcher will be disabled, and all of the allocated space for metadata will be freed. RnR programming interface does not need programmer to modify the kernel of applications. Programmer only need to insert the RnR control functions to programmer faces with long of repeating patterns and select the target addresses. Now we have described the responsibility of the programmers when using proposed RnR prefetcher. Next, we describe the hardware responsibilities for controlling the timeliness of the prefetches. The desirable prefetch request should be issued close to the demand access time so that demand access can hit in the cache. But the prefetch data should not stay in the cache for too long before the demand access arrives. Early prefetch can cause cache pollutions and prefetch data can be evicted before it is used. The key to timing control is to control the progress of prefetching relative to progress of the applications. The proposed prefetcher uses length of cache access to approximate the progress of the application execution. This time control does not need to be precise. Therefore, a timing window is used as the observation granularity. During recording, a window is determined by having the same number of misses, and the length of access within this window is recorded. During the replay, the prefetching speed will control by observing the length of cache access during each window. The window moves when enough access are observed, and the prefetch outside the current window have to be waited. Double buffering is used to prefetch one window ahead of the execution. This is because prefetching takes time to return data from the memory. In this work, The proposed RnR prefetcher is placed in the private L2 cache controller in parallel with the L2 streaming prefetcher. RnR record misses from L2 cache that are within the target address range at record iteration, and prefetch data into L2 cache during the replay iteration. RnR requires to add both software visible registers, which are state and window size registers, as well as internal control registers, which include a counter for lamp of access and a current window lamp register. The division table buffer and the sequence table buffer are used for grouping metadata writes during recording and prefetching metadata during replay. The division table is used to record window boundaries, and the sequence table requires miss addresses. In the following slides, we'll go through a simplified example of how to record and replay. The prefetcher state is set to record through programming interface mentioned earlier. A cache miss will check whether its address is within the targeted recording range. If not in the target range, the miss address will be sent to a streaming prefetcher. If in the target range, the address will be stored in the sequence table buffer. When the sequence table buffer is full, the miss sequence will be written into the reserved memory space to divide the memory sequence into multiple windows. Once the predefined number of misses are recorded, the X counter value will be recorded into window division table buffer. Similar as miss sequence, the window division table buffer will be written back when it is full. In this example, the window size is 2. 4 misses A, B, C, and D are divided into 2 windows. Value 40 and 90 in the window division table means the lamp of access during the first window and the second window respectively. After the prefetcher state is set to replay, the RnR prefetcher starts to prefetch metadata from memory and use the stored miss sequence for prefetching. In the meanwhile, the counter records the number of access during each prefetch window. When the counter value is equal and greater to a window division value, the prefetch window advances to the next one and prefetch one window ahead for double buffering. When all of the prefetches is issued within the current window, the prefetcher will pause and wait for the access counter to catch up with the recorded lamp of access during the window. For detailed description of the record and replay iteration, please refer to our paper for more information. To evaluate the proposed RnR prefetcher, we use a cycle-accurate simulator to model a system with 4 out-of-order cores, and RnR is placed at each of the private L2 cache. We evaluate 3 iterative algorithms with 8 different real-world data inputs. The data inputs covers a wide range of sparsity and sizes. For performance, the proposed RnR prefetcher alone can achieve in average a 2.16 times of speedup for graph applications and 2.91 times speedup for an iterative solver sparse CG as compared with baseline without prefetcher. When combining the RnR prefetcher with a streaming prefetcher that covers streaming access, RnR combined achieve a performance close to the ideal case, which has no L2 cache misses. The prefetching accuracy is the number of useful prefetchers out of the total issued prefetchers. RnR can achieve an average of 97% of prefetching accuracy. This is because replay iteration will have exactly the same miss sequence as the recorded iteration. By matching prefetching speed with the demand access speed, most of the prefetch data will be used before eviction. The miss coverage refers the percentage of misses that a prefetcher can reduce. The proposed RnR prefetcher can detect all of the miss sequence within the target data structure without sharing the patterns and data dependencies. In the evaluated workload, irregular access to the target data structures cause most of the misses. Therefore, RnR can achieve an average of 91% of miss coverage. Besides the coverage and accuracy, timeliness is also essential to the effectiveness of prefetching. Without proposed timing control mechanism, more than 98% of prefetches are prefetched too early, that are evicted before demand access. With timing control, more than 97% of issued prefetches can return on time. The proposed RnR prefetcher has a relatively low off-chip traffic overhead. As compared with other prefetchers, RnR has a high accuracy, and hence most of the extra traffic generated by RnR prefetcher is due to metadata prefetching. For storage overhead, the metadata size is on average of 12% of input size. To conclude, a software-assisted hardware prefetcher is proposed to improve prefetching accuracy and miss coverage for the application that has long repeating irregular memory access patterns. By allowing programmer to decide when and what to record and replay, the proposed RnR prefetcher can efficiently record mid-sequence of the target data structure and prefetch through a replay in a timely manner. We invite you to join our live talk at Micro 2020 for more discussions. Thank you.